So before, what we looked at? We had looked at the idea of searching where you were at a particular place, you were trying to get to a particular goal, and the steps that you went through along the way were important, right? The path cost mattered. We said in some kinds of problems, though, the path cost doesn't matter. All you care about is getting there. It doesn't really matter how long it takes you or what the route that you took. But in the cases where the path matters, that's where we're using things like A star and so on, those kinds of algorithms that tell us how to get from here to there following existing available paths. But other kinds of problems, we just care about getting to the solution. And we don't really care how we got there. We just want to get there. So we have these idea of looking at the solution space and searching through the solution space for answers, but not necessarily worrying how you get from one choice to another choice to another choice. But what do you have to have if you're searching through a solution space for answers? You have to be able to determine that this one is better than that one, right? This possibility is better in some way than some other possibility. And so the idea is we are going to, with one approach, this approach of genetic algorithms, we're going to mimic kind of evolutionary biology, what happens in terms of being able to create new solutions from old solutions. And hopefully those new solutions are better than the old solutions. Not always. And sometimes the new solutions can lead us down a bad path to where the solutions get worse and worse. But when the problem is carefully presented and when it is presented or when it has a solution that is appropriate for this technique can be really nice. So we can solve problems that would otherwise take us a lot of work. We can also, in applying genetic algorithms, I've seen genetic algorithms applied to um, a bunch of different kinds of problems. One that had to do with satellites, small satellites that when they get into space need to unfold so that they can, have the solar panels and everything, but they need to be packed small to get there and then unfold. And the way those are designed can have a big effect on how efficient they are in terms of unfolding and how small they can be made and so on. And so I've seen some genetic algorithms that do that design and come up with some things that people just would never have thought of, or at least people had never thought of before. And then when the algorithm created these solutions, it's like, well, that's really, really nice. And then other times you see genetic algorithms, again, just kind of spiral off and give you bad answers to problems. So sometimes that's because the problem wasn't worded correctly or formulated correctly. Sometimes that's because the representation of what a solution is wasn't formulated correctly. And sometimes certain problems just aren't set up to be solved in this particular method, right? So sometimes it's just you can't just search through a bunch of answers and hope to find one. Certain things that doesn't work out. So what's going to happen with the genetic algorithm? With with a genetic algorithm, we often apply this to kinds of problems that are optimization problems, problems that there is like a you're looking for the biggest something or the smallest something, right? You're trying to find a particular value, or you're trying to satisfy certain constraints in a certain way. You have to satisfy certain conditions. So satisfying those conditions is a positive thing, and not satisfying them is a negative thing. And so what usually happens is in a problem that we're going to try to solve in this way, we have to somehow be able to, if not quantify solutions, in other words, if not put a numerical value on them, at least be able to compare them to say this one is better than that one, right? So some way of being able to say this is a better solution than that solution. And so what we do to mimic the idea of biology is we will, after we've designed or described our problem, right? So we have our problem description, and we're again thinking of it in some way that maybe we can have. this comparison between potential solutions. Um, we want to represent potential solutions in um, this representation of potential solutions. We're going to, again, mimicking the idea of biology, we're going to call those chromosomes. We don't always call them chromosomes. Some people do. But what happens is we have a solution that has aspects to that solution. And so the whole solution altogether is a chromosome, or again, a member of the population, sometimes is all that's said. But you have values in different positions in your representation. And what we would then do to mimic biology is we pick two members of our population, or two chromosomes, and do something where you pick part of one of them and part of another one and put it together to get a new potential solution. All right, so we have this potential solution gets some kind of calculated value of how good that solution is. And this potential solution has some kind of calculated value of how good that one is. And if we put two of these solutions together, we create a third solution. Different ways of doing this, lots of different ways of doing this. But creating a new solution from here with the hope that we can kind of inherit the good parts of the first one and the good parts of the second one to create an even better solution. Now, what happens? Do we always get a better solution? No. Sometimes we get exactly the same solution that we already had. Sometimes we get a solution that's even worse than the ones that we started with. So the process of genetic algorithms is to think of different ways that we could join these together and different ways that we can um, um, expand or continue improvement among potential solutions. All right, so we'll have a problem description. We're going to represent our potential solutions in some way like this. And we will then also, as part of this, we need some kind of fitness function, a fitness function that is easily evaluated for a particular chromosome or a particular potential solution. So we want something that's easy to evaluate, but that is also meaningful in the context of what the problem actually is. All right, so there's a lot of, there's some science to it, but there's also a lot of kind of art to it, of how do you, some people might even say black arts to it, right? So some magic going on, right? Of how do you make this work to present or to find good solution to existing problems. All right, so as an example, a situation where we would not use genetic algorithms is going to be our first sample, our first lab on this topic. We will play Mastermind. All right, so what do we have? We're going to have some numbers, and we have to guess those numbers. All right, so we're going to create a system that will be able to create or find a solution. All right, now, so let's just say that the numbers we were looking for are 1, 2, 3, 4, but we don't know that. All right, we don't know that. The algorithm doesn't know that. Externally, something knows that, but the algorithm doesn't know that. So let's say we're looking for this. A representation of a potential solution would be what? 4 numbers. And so we might have that as some potential solution? Well, the fitness function needs to score this potential solution. It needs to give us some information back about this potential solution that says this potential solution gets a score of something. Again, we're not going to use this in real situations because in real situations we don't know what the answer is. Right? If we knew the answer, we don't need the genetic algorithm to find it. But we would have this kind of idea, something that we're trying to achieve. And so maybe the fitness function measures something different, but this time it's going to be very specific. So what could the fitness function measure in this case? We could say how many digits were correct, or we could have something to do with the difference between the digits. We could get some kind of calculation there. We could say how many digits do you have that are the correct digits but not necessarily in the right spot. Right? So we could have different kinds of fitness functions. So depending on what fitness function you come up with, you might get different results from your algorithm. So if we just said, how many correct digits do you have, what might you say in this case? We might say there are 2 correct digits because you have a 2 and a 3, but none of them are in the right spot. Or you might say, well, how many are in the right spot? None of them. Or you might have some more complicated fitness function that says 2 in the correct spot, but 0, 2 correct numbers, but 0 in the correct spots. Right? So you could have a fitness function that would give back multiple pieces of information, possibly. But we want to be able to compare 2 fitness functions. So if we just said, how many correct digits do you have? Then we have 2 correct digits. And so this potential solution would get a score of 2. All right, let's say that's another potential solution because we don't know that they're all different digits. All right, so what happens in terms of the genetic algorithm approach is we're going to look at these 2 solutions. We're going to say, okay, let's say these are 2 that we've chosen, 2 potential solutions, 2 chromosomes, and we're going to create an offspring from there. How could we go about creating offspring from here? So the initial idea of a genetic algorithm is new potential solutions come from merging 2 existing potential solutions because that's how biology works. It was based on biology. It turns out in a lot of situations that merging more than 2 parents creates better outcomes. So having 3 parents or 6 parents, depending on what's going on, might give you better solutions more quickly. Okay. Um, we step away from the biology a little bit. You still have the biology um, kind of idea behind it. So originally it was trying to create this biological aspect and saying, let's take 2 and create another one. And then take 2 more, or maybe 2 of the same, and create something different from there. So one approach, there's lots of different approaches, and again, we're kind of jumping into the middle of it because now we're going to have to come back to a lot of extra pieces. But one approach is, sorry. Okay, so one approach, it might be the way it happens in a lot of situations. You look at this particular um, gene on the chromosome, and it has 2 different values, and we pick one of the values. We say 50-50, right? Pick this one or that one. Go to the next one, do the same thing. Go to the next one, do the same thing, and keep doing that. Now, what happens in this case? We could, depending on how that happened, we could get different values, right? We could get different results. Because you might get 2 here, and then you might get a 0 there, and then you're going to get a 2 and a 3 in those. Or you might get 0, 3, 2, 3. Or you might get 0, 0 again, 2, 3, or 2, 3, 2, 3. So you might get one of the original parents back again, or you might get something different. What happens with all of these? This score was a 2. This score is a 2. This score, still a 2. Still a 2. And the other 2 possibilities are still 2s. So, I'm sorry? Yeah, so based off our current fitness function, based off... well, no, so how many correct values do you have? Well, it says you have a 2 and you have a 3. Right? You have them multiple times, but you have a 2 and you have a 3. Now, allowing duplication, this one then might be considered to be correct because you have a 2, but you don't have a second 2, so this one wouldn't be correct. Or so again, but what happens in this situation if we use the other measurement, the other measure that says how many are in the correct spot? Zeros across the board, right? None of these are in the correct spot. So all of these solutions give us zeros. Even though we have 2 of the right numbers, none of them are in the correct spot. So again, depending on the fitness function, you will get different answers and different things will have to happen. Well, from this starting value, from these 2 starting values, can we ever get to that answer? Right? With breeding in this way, we can never get to 1, 2, 3, 4 because we don't have any 1s and we don't have any 4s. So what do we have going on with genetic algorithms? We sometimes have mutations that occur. So a mutation can occur that we create an offspring. Let's say this is an offspring. And then we pick one of those genes and just change it to something else in some random kind of way. Yeah, so there's all different kinds of what the mutation might look like. So we're going to go into a lot more detail. But just as far as the idea of mimicking reality, right? Here's the offspring. Oh, wait a minute. There was a mutation in one of the genes. And so what happens? Maybe the mutation is a good thing, right? Maybe in this particular case, maybe that becomes a 1. If that becomes a 1, what happens? Our score goes up. But what if that becomes the 1 instead? Well, if that becomes a 1, our score still goes up, right? Because we still have a 1, a 2, and a 3. Right, so the score still goes up. So it can be a different 1 and the score still goes up. Again, with the fitness function of do you have the right numbers? But what if that one became the 1? It stays the same, right? Because we have 2 1s, or 2 2s and a 1, and the fitness score stays the same. All right, so what can happen? We don't just have to have individual by individual like that. We can have different ways sometimes that we combine. One way of combining is called crossover, a one-point crossover. So one-point crossover would take 2 parents, and then let's say we want to do this. Let's say we have our point right here. What we would do is we can create 2 offspring from here. One of them takes the first part from here and the second part from the other. And the other one then takes the first part from the second one and second part from the first one and does this, which does what in this particular case? Nothing, right? It doesn't improve anything. But sometimes what might happen? Sometimes you might get an improvement, right? Because you might have something that's in the wrong place on one parent and in the wrong place on the other parent, but when you swap them, now they're in the right places. And so you can get an improvement. But in this particular situation, that particular one-point crossover method does no good for us at all. But there are lots of other variations on this with genetic algorithms. We can do a lot of different kinds of modifications to start with a potential answer or a potential set of answers, or, well, a set of potential answers, put it that way, a set of potential answers, and combine them. And what's happening here? This combination is a really quick process because really it's just bitwise operations. And then the fitness function needs to be something that can be calculated quickly, so it's calculated quickly, and so we can tell did we get an improvement or not. All right, so then what happens? Continuing with the idea of um, genetics, what do we expect to have happen? Well, we have a population that we've started with, not just two things necessarily. We have a population that we've started with. So an initial population. And now we've gone through this process, and what do we have? We have more things in the population. Right? We've added some. We had the original population, and now we've added some new potential solutions. Well, what might we do? We might have some of the population die off. It can die off in lots of different ways. We can have less fit solutions kind of removed from the pool. We don't want to do that in real life, right? That is not, but that happens in like animal populations and things, right? Things that are less fit do die off, and they don't carry on. Their genes don't carry on to later generations. Um, so we might disregard some of the less fit solutions, but we might want to keep some of them around because some of them might be nice for. They might have certain things going for them, right? We might have something that has a really low score, but it has a 1 in the right spot, and we're looking at what's in the right spot. So you might want to keep some of the lows, has everything else wrong, but there's that 1's in the right spot. So we want to keep that one around, even though we don't know we want to keep that one around, right? So in the population, we have the original population, and then we have the new additions, and we look at that whole thing, and before we breed again, we decide some way of determining which ones carry on. So which members of the population are going to be allowed to continue? Sometimes it's just based on age. This member of the population came into the population at this time frame, and it can only be active until this time frame. Sometimes certain versions of the algorithm, you might say each generation just create as many new things as you had originally and get rid of everything that you had before. And just go with the new things. Sometimes you might do something if you rank them in fitness score and keep the top 50 fitness scores. Lots of different methods. Sometimes it's a random selection. We'll talk about pros and cons of all these different ways of creating your next cycle of population. And so what happens, we are searching through the set of all possible solutions, looking for the actual solution that we want. We don't care how we get there. What do we care about? Maybe we want to do it as quickly as we possibly can. But we don't care about, okay, well, we went from this member of the population to that member of the population to this member. That's not the part that matters in this kind of search problem, right? In this kind of search problem, we're trying to find an answer amongst a set of possible answers. And so we have this approach gives us a way to represent different answers and then to compare those different answers. And then not only that, but to be able to create new potential answers from those. All right, so generally what will we do is we will have our population that we will create originally can be a random collection of things that fit whatever our potential solution representation looks like. Um, or maybe we have some kind of idea of what a good solution might look like. Now, for Mastermind, we don't have any idea of what a good solution looks like, only that it's numbers and how many numbers there are. So we might have just a completely random a seed for the population, but we might also have a heuristic based. Says for this kind of problem in the past, these kinds of answers have been pretty good. So let's start with some of those and then add some other things to it. Um, Another question is how many things should you have initially? So if we look at, we know there are 4 digits and repetitions allowed. How many different solutions are possible to this particular game? How many solutions are possible? Well, how many digits are there? 10, right? 0 to 9. So, well, 10,000, right? Because it could be all zeros or all nine. So what do we have? 10 options at each possibility. 10 times 10 times 10. There are this many solutions. So what would happen if you created a population of size 10,000? Well, the answer is one of them, right? Fitness function, especially if we had the fitness function of how many do you have in the right slots, one of those is going to have a 4. All right, but the point is to avoid brute force checking everything, right? So with 10,000 possible answers, maybe we start with an initial population of, say, only 10. Just randomly generate 10 things and see what happens. All right? Now, if we know 1, 2, 3, 4, then it defeats the whole purpose, right? So the idea is in a genetic algorithm that we're creating trying to solve a real problem, we have to figure out what our fitness function is going to measure so that we know what a good solution might look like, even though we don't know what the solution is. So for the fitness function, from the algorithm perspective, it just gets back a number and has to do something with that number. Right? It can't know that 1, 2, 3, 4 is the right answer. So these have to be separated. In implementation, those have to be separated. The fitness function comes in from outside. The score comes back from outside. The algorithm can never access how that score was obtained other than here's a sample. Oh, there's my number that goes with it. Right? So the fitness function has to stay inside a black box. Right? Just input something, get something back. Can't know what's really going on. All right, so let's just let's. This is probably a bad idea to make up some numbers and to try with to say 10, and just using the 1 point crossover and see if we can come up with 1, 2, 3, 4 in a few generations or not. All right, so we're going to select some numbers. Um, and I'm not going to let you make them up because I know how old some of you are. Um, so, so either a random number generator or we can just go with some phone numbers, right? Last 4 digits of phone numbers. So, Bash, give me the last 4 digits of your phone number. Okay, last 4 digits of your phone number. It's 30. Wait a minute. Okay, go ahead. Is it real? Okay. I'm not seeing a good 1, 2. There's a 3. Oh, no, okay. So all the numbers are here. All the digits are in here. All right? The ones that we care about. So there's a 1, 2, a 3, and a 4. I don't think we had a 4 until... No, we did have the 4 there. 1, 2, 3, 4, 5. We have 7. We're going to stop, right? Because we have enough pieces just to see how this would work. All right. So what's the score of the fitness function score for this? So let's use the one that we had started with originally that says how many numbers are the correct numbers. All right, so this one has a 1. If we had the other score, this would be a 0. All right, what about this one? This one's a 2. This one's a 0. It's a 1. And this one's a 2. Okay, so what might we do? We might... Well, let's go ahead and pick some parents for creating new offspring for the next generation. What might you do? We might think, well, let's pick the most fit parents. Right? Let's pick these two. But we might not want to just pick those two because what do these two give us? These two could potentially give us, they could potentially give us a 1, 4, and a 3, but they still can't give us a 2, right? So we don't want to just completely rule out all the others because we don't know what they have going for them. So we might want some of the others to stick around as well. All right, so let's take those two, though, and just see what might happen. If we do the 1-point crossover, again, at the middle, just because that's where often we do it kind of by default the first time around, what offspring can we get? We would get 3, 0, 4, 1. We would get 0, 7, 1, 0. All right, so in that 1-point crossover, we're going to create 2 offspring each time. What's the score for this one? This score is a 3. This score is a 1. So what happened? We put 2 2s together, and one of those solutions, or potential solution, went down in fitness, and the other one went up in fitness. If our fitness function was how many were in the right spot, we could end up with all 4 of the right numbers but in the wrong order, and it actually looks worse for that fitness function, but it looks better in the other situation. All right, so what would we really probably want? We might want both pieces as part of our fitness function, right? But then we would have to be able to compare. Is this a better function than, or a better score than this, or a worse score? Does that make, what would this mean? This would mean you have 4 of the right numbers, but none of them are in the right spot. And this would mean you have 2 of the right numbers, one of which is in the right spot. So which of those is a better solution? Well, we'd have to figure it out, right? We would have to decide which of those is better. We would have to determine for the particular problem, which would you rather have? Again, knowing that we can't take a solution and do anything else with it. All we can do is keep reproducing, right? That solution with other solutions. So which solution is better? I don't know. We'd have to think about that. Which one do you want to leave in the population? If you had to choose between them, which one do you keep in the population, and which one do you remove from the population? All right. So so we have created a new member, or 2 new members of the population right now. If we have a regulation of a fixed population size, what does that mean we have to do? It means we have to eliminate 2 members of the population to allow these 2 new ones in. So if we have a fixed population size, we have to do that. And what would we eliminate? Right, we probably would choose this one because nothing matches, so there's no reason to keep it around in this context. But then we have to get rid of 1 more. And if we randomly select one of the ones, we could potentially get rid of the only, this time we had two twos, but we could potentially get rid of the only one that had a 2 in it. And so we could accidentally eliminate any chances of getting to the right answer. Does that make sense? So, but we can't, all we can eliminate based on at this point is on the score, because we don't know that it's the 2, right? But you're saying a fitness score of 2. We're saying, well, what if we just go ahead and eliminate something that had a higher score? Sometimes there would be a good reason to do that, right? We say, okay, well, these have already created offspring. Let's get rid of them. Maybe those are the ones we get rid of. But there's a lot of choices and a lot of why you want to do this in this case and why you don't want to do it in other cases and so on. So there's a lot of details here, right? But your approach, you said, was let's get rid of that one, and somebody said just randomly pick one of the ones. So if we randomly pick one of the ones, let's say it was that one that got taken out. All right? So we don't like that because we see that 2 was in the right spot. But we still have a 2. We still have a 2 floating around up there, right? All right, so now what's our population look like? Well, I guess we could have gotten rid of this one as well, because it was one of the random ones now. Don't really let it get into the rest of the population. All right, but we've done the same kind of thing with other pairs as well. So maybe we've paired up other things, so there's even more offspring to consider. So there's even other things that could have been eliminated. Maybe this one didn't have to get eliminated because some other of the offsprings also had 0. So maybe they got eliminated instead. All right, so now we have the new population. And let's say we happen to pick this one and this one. What happens? One of those in the same method looks like this, and the other one looks like this. And what happens? We get a 1 and a 3. But now we've lost the 3 again, right? And so what happens if we're just using this particular kind of crossover with these particular values? Will we ever get to 1, 2, 3, 4? Can we ever get to 1, 2, 3, 4? Well, we need... So, I mean, even can we get the numbers even in the wrong order? Because what's going to happen to get a 3's at the beginning and a 2's at the beginning, and we need both of them, and we can only get one or the other, can't we? All right, so what happens is no matter how well we design all of this and how great our fitness function is and since our starting values were random, well, I mean, arbitrary at least, right? That we can't actually get to a solution, even in the wrong order from here. So this is where the other features like mutation can come into play. That maybe sometimes, not very often, but sometimes we say, okay, we've created an offspring. Let's just change one of its values. The first approach of going gene by gene, well, what would happen in going gene by gene? We still could only get a 2 or a 3. We couldn't get both of them just because of the particular values that are here. Could we get a 1 and a 4? Yeah, we could. If we happen to put these two together, we could get a 4 and a 1 from there. So we could get a 1 and a 4, but we can only get either a 2 or a 3. So what happens with mutation is sometimes you can say, hey, let's change a value to a new arbitrary value. Well, sometimes that's worse, but sometimes you just get lucky and happen to allow the right thing in. What happens if these were binary rather than decimal values? Sometimes you just flip a bit. Just one bit just arbitrarily changes from a 0 to a 1 or back. Or you can completely flip all the bits. Everything just gets flipped. All the zeros become ones and all the ones become zeros, and sometimes that's a better solution. Sometimes you have something that looks really bad, but it's kind of close to a good solution in that sense, that it's kind of the opposite of a good solution. But sometimes the opposite of a bad solution is just another bad solution. Right? So having that possibility, though, but we can't wait and be like looking at what the real answer is and saying, oh, now let's do this. Right? We have to decide all this ahead of time. We have to allow these possibilities, because what happens in real scenarios, we don't know that. Right? And we have no way of knowing that. We have no way of knowing what the right answer is. We just have a way of comparing two potential answers to say this one is better than that one in some way. So we go through the idea of how do we choose the parents? There's lots of different ways to choose the parents. How do we create the offspring? What happens in the mutation? And then that idea of survivor selection, of determining which members now make it into the next round. And the algorithm then starts. Right? We just start letting it chug away at these examples. Then what has to happen? The algorithm has to eventually stop. Right? To be an algorithm, it has to eventually stop with some kind of answer. So when could we stop? Right? If we get 4, we can say, hey, I got all the right numbers. They might not be in the right order, but that fitness function doesn't care. So if you get to a 4, you stop. You say, hey, yay, I've got them. Right? When else could you stop instead? Yeah, we could say, okay, we're going to do this for 1,000 generations, then we're going to stop. Or whatever, right? Some arbitrary, some set number of generations that we've determined ahead of time. And what is our answer going to be? Whatever the best answer we have at that time. Or maybe the best answer that we found along the way. Because sometimes, depending on what other kinds of aspects we have in our population, maybe a really good answer died off a few hundred generations ago. And maybe that was the best answer we had found ever. But so we might say, okay, that's the best answer. Or we might say, whatever the best answer that we have right now. Again, that depends on the other construction of the problem. How else could we decide to terminate? So if you find the right answer, right, find the maximum value that it can possibly be. Or if we say, all right, after this fixed number of generations, this is the best answer we've found. What else could we say as a termination point? Yeah, if we've got a certain number of generations with no improvement, we might say, okay, we might be stuck in a rut, or we might have found the best answer. We don't know. We could say, well, if we've done enough generations to have calculated possibly every single example, right? If we've ended up brute forcing our way through, I guess we could go ahead and stop, right? But usually we have an infinite solution set, right? The space is an infinite space. Or it's so big that we're never going to try everything. But yeah, so what's the typical ways of stopping? If you achieve whatever you know is the best possible fitness score, if you reach your predetermined time period, say this many generations, or if you say, we've been going for 100 generations and there hasn't been an improvement, so we're probably not going to see an improvement, so let's stop. The only one of those that guarantees that we have found our answer is if you reach the predetermined value that you know is the correct answer somehow. But in real life scenarios, you almost never know what the right answer is, right? But sometimes we do. So in this particular case, even though we don't know the numbers 1, 2, 3, 4, we do know the best score you can get is a 4. And so the algorithm could go until you run into a 4. If you don't get a 4, then we could have the extra test to say, okay, if you've gone this many generations, just go ahead and stop. Or we could say, if you've gone this many generations without finding so we could combine all 3 of those, right? If you've gone this many generations without finding a new, better answer, then stop. Otherwise, keep going until you reach this many generations. But if before that you happen to find a 4, go ahead and stop. All right, so we're going to implement um, various aspects of all of this, of how you create the population, how you represent the solutions, how you score things by different fitness functions, how you choose to combine parents into new offspring, how you choose to eliminate them, um, what kind of operations you do on the combination. So all of those aspects change little things, and you can completely change the outcome. So what do we have? We have a search. We're searching through potential solutions. What is it really? It's really a guess and check. But it's an organized guess and check that's trying to figure out a way to pick out the best bits of different potential answers. Um, there's other aspects that we'll talk a little bit about. Um, Sometimes rather than having two parents, we can have more than two parents, or sometimes we can just have one parent. And so what one approach for one parent is what's called the Lamarckian model. You're going to it kind of corresponds to being able to transmit learned information to the next generation. So what you look at is you have a potential solution, and you look at the neighborhood of that potential solution. So the neighborhood is in some way of measuring distance, of not being too far away from that one. So maybe if you're within a certain value of each gene, or a certain combined distance from genes in terms of improving a score, you make these modifications to the chromosome, but you're not really making them. You're kind of theoretically making them. And then if one of those is more fit than the chromosome that exists, then you just make that one pass on. So it's like you learned something, and you can pass that on to future generations, right? Instead of just passing on what you were born with, you learned something. Pass that on instead. And so there's a modification that we can do to the whole process that does that. There's another version of that that says we look at the neighbors, and if there's a better neighbor, we don't pass it on. We still pass on the one that we have, but that gives us the idea that that chromosome has the ability to acquire that information. Right? It's pretty close to something that's good. So maybe with just the right mutation, it could work. So there's a lot of different approaches and a lot of different ways, and those match certain kinds of real life scenarios that aren't necessarily strictly biological, but that have biological ideas behind them, right? Biological tendencies or something, right? So systems that can mimic the idea of what happens. And so we will apply this again to mastermind. We'll apply this to our chess problem that we've talked about before. We have to think about what would a potential solution look like, and the potential solution has to be in this kind of, here's some values, or here's some pieces, and then those pieces are going to get put together in different ways. So um, we think about what that chessboard solution might look like. What would a fitness function be in that case? What kind of fitness function are you trying? What value are you trying to get to? Um, we'll do the same kind of thing with an expression. As you know, there's that idea that what is it? If you had an infinite number of monkeys and an infinite number of typewriters, you could create all the works of Shakespeare or whatever that is. Well, we're going to pick a particular Shakespeare quote and try to apply a genetic algorithm to generate that quote. Well, what would a random population member look like? Just a collection of a bunch of letters, right? Um, and Well, I'm going to give you a particular quote that we're going to try to generate using a genetic algorithm to see how well it can do. Again, what happens in real life, though, in the real life situation is going to be more like the chessboard problem, where you don't know what a real answer looks like. You just know the structure of a real answer, and we're going to let the algorithm find an answer for us. And then we'll talk about some other scenarios where all we know is roughly what a solution might look like, and in a lot of cases, we can still create a genetic algorithm to find that solution for us. So it just becomes a search through a search space that we don't care how you get there, just as long as you get there. All right. So we will spend a lot of time. Well, not so much more in class time, some more in class time, but a lot of time on the labs of creating the necessary pieces and implementing the various pieces. So in the um, next lab, I will give you a few algorithms to implement that we may have implemented previously, but that are useful and parts of the implementations here. So you'll kind of just build some functions that will do certain tasks, and then we'll put them all together to solve particular tasks in the context of this genetic algorithm structure. All right.